Okay, go ahead. Thanks. Thank you very much for giving me the chance to speak here. This is another talk in the neutron stars theme, but now on a much smaller scale. So we've had a couple of talks which were largely looking at the macroscale problem of a neutron star, and this is more zooming right into the sort of Fermi scale. So the goal for this talk is to describe how I think we may or may not be able to create a fairly simple microscale model for vortices and fluxtubes within the core of a neutron star. Okay, so here's my outline. I don't really like outlines, but here's my best attempt. So I'll give some kind of introduction. Given that we've had in the last 2 days 2 very good review talks of different aspects of neutron stars, I kind of feel like I don't need to give much of an introduction, but I guess I should say something. And then I'll try and motivate why I think having a microscale model might be useful. And then I'll ask, can we actually come up with one? What are the problems in doing so? Okay, so just to remind you of what we've heard in the last couple of days and also last week, we think that neutron stars, a typical neutron star maybe looks something like this. Basically, everything that we really know about neutron stars with confidence comes from observations of what's going on outside the star. Right? So we know that at least some neutron stars, i.e. pulsars, have dipolar magnetic fields that are tilted with respect to the rotation axis. We know this because we see these pulsars in the sky. So as the star rotates, we see its radiation beam sweeping around, and you get a pulse of radiation whenever you're hit by that beam. So by measuring the pulses, we are directly measuring the rotation rate of the star. We know that with high confidence and to extremely high precision, to the extent that we can often measure the spin down rate of these objects, from which we infer their magnetic field strength using this formula. P here is the period of the rotation. And we know how a tilted dipole emits electromagnetic radiation. So we think we have an idea of how the spin down is determined by the dipole component of the magnetic field. Okay, so that's the kind of stuff that we actually know. But the question really is what's going on inside the star. Here things get more uncertain because we don't really know the equation of state and so on. But we're pretty confident that the structure looks something like this. The star has a radius of maybe 10 or 11 kilometers. The outer kilometer is a solid that we call the crust. In that region, the ions are all trapped in a lattice, a kind of crystal, and it's only electrons that are able to flow. So the magnetic field in that region must be supported by currents of the electron fluid. So I've worked on this problem a little bit. And the problem that you have is that if you want to just model the crust in isolation, then you have to relegate the rest of the star to just some kind of lower boundary condition. And we know that in reality, the core of the star is not just a boundary condition, it's a whole problem in its own right. So I've been trying to understand what's going on in the core and how we might be able to model that. We know that within the core of the star, the neutrons and protons are both condensed into superfluids. I'll remind you that about 90 to 95% of the mass within the core is neutrons, but there is still enough protons hanging around that they can support currents and maintain a magnetic field. So both the neutrons and protons form superfluids, and the most important consequence of that is that the vorticity and the magnetic flux are quantized into discrete filaments, which I'll refer to as neutron vortices and proton fluxtubes. Although, as we've heard, because of the entrainment between the two fluids, the neutron vortices are actually magnetized. There's a circulation of, or a current of neutrons around each flux tube, and there's a circulation of protons around each vortex. So the distinction between the vortices and the flux tubes is not as clear cut as in more familiar two-component superfluids. But still, just to avoid any confusion later, if I refer to vortices, I probably mean neutron vortices. If I refer to flux tubes, I definitely mean proton flux tubes. Okay, so the first difficulty is that there's an awful lot of these things. We know roughly how many there are because we know what the quantum of circulation is. So if we know what the overall rotation and magnetic field of these objects is, then we can infer roughly how many vortices and flux tubes there must be. And we come up with ludicrously large numbers, 10 to the 18 seems pretty big, but in a way that's actually quite a small number. 10 to the 30 or 31 is definitely a very big number. And this tells us that for each neutron vortex, there's about 1 trillion or more flux tubes. So the way to picture this is that actually these 10 to the 18 vortices are extremely lonely. They live their whole lives and maybe never even discover that they're not alone in the universe, right? These things are actually very, very far apart. But they do know all about the flux tubes. They're constantly running into those. Okay, so given that we have somewhat large numbers of these things, it's not really feasible that we're ever going to be able to model all of them at one go. That's kind of what we'd like to do, but obviously that's impossible. So if we want to build some kind of macro scale model, as we've been hearing about in the last couple of days, the only realistic prospect of doing so is if we smooth over all of these vortices and flux tubes and develop some kind of microscale parameterization that we can then use within our macroscopic models. So such as the sort of HVBK model, for example. What makes this difficult is that we don't really know what's going on at the microscale very well. And this point has been made in earlier talks, but just to reinforce it, even quite basic questions we don't really know the answer to for sure. So we know that on average, the vortices must be aligned with the star's rotation axis. So the simplest thing they could do is just form a rectilinear array as suggested on the left. But in reality, we expect they probably form some kind of mess, such as shown here on the right. So this is from a simulation of rotating helium. And you typically find that these things become turbulent, they form a complex tangle. There's no real reason to think that in the core of the neutron star, the neutrons are all nicely lined up like this.
So these fluxtubes repel one another presumably with short distance interactions.
The vortices definitely repel each other. Here I'm talking about vortices.
With short distance interaction, or is there a long distance?
Long distance.
It's long distance. So
there's a long distance, there's power law.
Right. So yes, indeed. So they are at least not going to sort of clump together. But they may not
try to move to one another. Do they break apart, or do they not? Is it impossible to move one fluxtube through another?
Oh no, they can definitely pass through each other. They can reconnect. They can't break in the sense that they can't just sort of have an end in space. But they can reconnect.
They change, right?
Yes. So they can exchange as they pass through.
Right now, the interaction energy is small enough so that can happen.
Yes. There is a tension within the vortices, so they probably would like to straighten out if nothing else is affecting them. But when you've got if you've got a high enough complexity in your flow, it seems kind of almost inevitable they'll tangle up. And there's arguments for how there can be instabilities as a result of interactions between the neutrons and the protons, for example. So there's a lot going on which could lead to a tangle on the right. And we know from experiments in helium, it's not very difficult to tangle up the vortices. There's really no good reason why they should remain perfectly straight, as shown on the left. Nonetheless, an awful lot of the models of the neutron star core assume that you have a perfect.
If they can break, then they can straighten out, can't
they? They can straighten out, but the time scale on which they would do so might be very long. Especially if you bear in mind these are lines which are like 10 to the minus 11 centimeters across and 10 kilometers long. Right? I mean, it seems to me utterly implausible that they're going to be
size scales. So in small size scales, it probably does straighten out in a large size. So it's like a viscosity or something like that. Reynolds number or something.
Right. Yeah. If the disparity of length scales, it makes it kind of inevitable.
Perhaps the best way to say that is that you expect dynamics to be regular unless you have a reason to suspect an instability. So if you indicate an instability, it will become chaotic, but otherwise you would expect it to be this regular structure.
True, there are many instabilities that are quite possibly present in the core. So even if it somehow started out perfectly straight as on the left, it would almost inevitably end up like this.
How does this turbulent picture jive with the very low density of the vortices?
Good question. I mean, there is such a disparity in length scales here. I mean, these are really, really thin objects. The typical separation between them is like 5 orders of magnitude larger than their width, right? So, I mean, definitely it's not going to look quite like this unless somehow you imagine these lines are much, much thinner than I've drawn them. I don't know. Honestly, I'm not sure anybody really.
Maybe one thing one can say is, although they're far apart, but the size is still very large. So they're far apart on the length scale of 10 to the power of 3 centimeters or so. Or
Vanessa, what was a typical separation between things? 10 to the minus 5 centimeters?
Minus 3. But the length scale is 10 kilometers. So
yeah. So there's many orders of magnitude between the width of one of these lines and the distance between them, and then there's many orders of magnitude between distance between them and the length of the lines. So there's plenty of room for interesting dynamics. In that sense, the Reynolds number is like astronomical. Okay, so this is my motivation. Okay, just to remind myself what this slide was supposed to be saying. My motivation for doing a microscale model is that we can't really have a macroscale model until we understand the microscale. And at the moment, I don't think we really do. When you throw the protons into this picture, it gets even more complicated. Right, so I have an applied math background, and my motivation is always to try and find the simplest model for everything that includes only the physics that I absolutely have to have. So what's the simplest possible model for a superfluid? I think the answer is, on the microscale, it's the Grove-Platevsky model, in which we write down a free energy that has a functional form like this. Psi n is our order parameter kind of wave function for the neutron fluid. So that's just a complex scalar field. And then we identify the superfluid density and superfluid velocity in terms of the modulus and the phase of that complex scale. For the proton fluid, it's a little bit more complicated because, of course, it's charged. So it has to be coupled to the magnetic field via the magnetic vector potential A. So the standard way of doing this is with the minimal coupling as in the Ginsburg-Landau model. So it's basically the same thing, except that now there's an interaction between psi p, the order parameter for the protons, and A, the magnetic vector potential. Plus, of course, we have to include the magnetic field energy in the model. And we have to slightly modify the definition of superfluid velocity for the protons. So the gradient of the phase is really the canonical momentum, which is kind of the sum of the superfluid velocity and the vector potential. Right. Of course, it's the circulation of this quantity which is quantized, which is why the proton vortices are called fluxtubes, because they basically carry a quantum of magnetic flux. Okay, so if we could model these two fluids independently, this is the kind of thing that we would need to do. But where things get interesting is when they're coupled together. And as we've heard quite a lot about in the last couple of days, the most important coupling between these two fluids is mutual entrainment, which is a somewhat subtle type of coupling that's not seen in that many systems. And it's extremely important in neutron stars. I think what kind of makes it difficult to imagine doing laboratory experiments that are directly relevant to neutron stars is the difficulty in having A, entrainment, and B, magnetic fields. Those are things which are hard to get into laboratory experiments.
What is the temperature within the core of the neutron star?
Maybe 10 to the 6, 10 to the 8 Kelvin.
10 to the 6 Kelvin?
Yeah, but the critical temperature is 10 to the 10 Kelvin.
All right.
So 10 to the 8 Kelvin is extremely cold.
Very cool.
The thing to compare is, the chemical potential to the thermal energy, right? So although that sounds like a high temperature, in terms of energy, it's actually kind of negligible.
So, but you still expect to have some normal fluid for this super fluidity?
In the usual sense of normal fluid, no. In the sense of like thermal excitations in the superfluid, basically there's probably nothing apart from in the cores of the vortices and the flux tubes. So in the usual sense of normal fluid, no, there's basically no normal fluid here. Having said that, there are electrons, which I haven't mentioned yet, but say something about later. And they don't condense, so the electron gas is a normal fluid. Okay, so the reason that entrainment is really important is it means when you have a neutron vortex, for example, the circulation of neutrons around the neutron vortex entrains the circulation of protons, which magnetizes your neutron vortex. That means that you can now have electromagnetic interactions between the neutron vortices and the proton flux tubes. And this has been recognized for a long time. It was pointed out, I think the first person to point this out was Saul in '89, that this can cause the vortices and the flux tubes to pin together, basically because when you calculate the magnetic energy of them separately, it's higher than it would be if they pass through each other. So,
what do you mean by electromagnetic interaction of the neutrons?
I don't mean of the neutrons, I mean of the tubes. I mean, a neutron vortex has a magnetic field.
No, I understand what the electromagnet is for the protons is, but what does it mean for the neutrons? The only thing that you can couple really is the magnetic moment. But since they are unpolarized, you see, so basically there is no coupling there. So how are you going to couple them? You see, electromagnetically, I don't see how you can couple them.
Because a neutron vortex has a magnetic field. Not because of the neutron's magnetic moment, but because of the entrainment of protons around the neutron vortex.
But where did the entrainment comes from? That's
so the entrainment comes from the residual strong interaction.
Okay, so that's another term which you're going to add somehow, right?
Well, we have to add entrainment in the model somewhere.
Yes, also. So you're going to tell us about it, right?
Yes.
Okay.
In fact, I have multiple slides.
Now, the question is, you say that vortices are pinned to flux tubes.
Yeah.
Why one is pinned to that and not the other way around?
Oh, because of language. What I mean is, that's why I put it in quotes. People tend to use the word pin, but I think it may not immediately clarify what's going on. What I'm saying is, if this is a vortex and this is a flux tube, the energy of this state is higher than the energy of this state. That's all I'm saying. So if they have a choice between intersecting or not intersecting, they will intersect.
Why is that the case?
When you calculate the total magnetic energy of those two states, this one has less.
The size of the flux tube is much like the neutron. Vortice is core, right?
Not necessarily. It sort of depends on where you are in the star. It's quite dense.
No, but the core, you have more neutrons than protons.
Yeah, but it doesn't follow that the core sizes are different. It just means that one's more dilute than the other.
Yeah. But and then you have one kind. Do you have really super neutrons? Yeah, but anyway.
Okay. Okay, fine. So basically, there hasn't been very much effort to actually model this in 3D. Right? So this idea of pinning, or whatever word we should use, between vortices and flux tubes has been around for a really long time and has been kind of accepted. But as far as I'm aware, the first model that actually looked at it in 3D was by Lisa Drummond and Andrew Malatos fairly recently. Andrew Malatos presented some results from this model in his talk last week. Here's a typical picture. So what we have here is proton flux tubes in blue and neutron vortices in red, and you can't really see because it's hard to visualize things in 3D, but basically in many places the red vortices are intersecting with the blue flux tubes. This is kind of important because if one sort of lattice or array wants to move with respect to the other, then they're kind of restricted. You can kind of slide along a flux tube here, but you can't easily decouple yourself from.
So entrainment is the energy when they're sitting on top of one another is less than
entrainment says that given the choice, the two superfluids want to move together.
But can you think about that in terms of an energy of the?
You can definitely think of it in terms of energy. It says that. Well, next slide. Oh, not next slide, but I will get to it.
You said 2 dimensions. So you might think there would be some kind of bound state or something like that.
Well, yeah, it just says that when the system is trying to minimize its energy, it will try and find a state in which the two fluids flow together.
Okay.
So when you have a vortex, you're probably going to get a circulation of the other fluid as well.
But there is another problem there. You see, if you have a neutron vortex, the next one is far away, so you neglect them for a while. And you have a trillion flux tubes.
Yep.
And if I look at the velocity created by the neutron vortex, there are so many flux tubes there. The velocity is all over.
Yep.
So then where is the entrainment? Because I have all directions.
Okay,
there is
so
a coupling, but I don't see entrainment.
okay, so it's fair to say that we tend to talk about how the neutron vortices entrain protons. It's equally true that the proton flux tubes entrain neutrons. So as you're saying, when you're looking at the velocity of the neutron fluid, you may not really care about the neutron vortices. It may be primarily determined by the flux tubes and the entrainment there. So it's a complicated picture, that's for sure. And it's also worth pointing out. So
they might impede entirely the formation of the neutron vortices. If there are so many there, they go in all directions, right?
They can't impede.
Unify.
Okay, they can't prevent there being neutron vortices. There must be neutron vortices by the Feynman rule, right? You know this is a rotating object. You know the quantum of neutron circulation. There just must be at least 10 to the 18.
No, but that conclusion comes from assuming that you have a single neutron, the superfluid.
Even with both of them and entrainment.
And how they're going to be two together, I mean, for vortices, whatever, that's not entirely obvious.
You can generalize the argument to the case of two fluids that are entrained, and you basically come to the same conclusion. You can't get around it that way.
Okay.
Yeah, I take your point, but you can check, and it does work out.
Okay.
Okay, so this model is really the state of the art in the sense that I think it's the only model I've seen that really does this. But also it is also
The current ignorance.
But I think it's fair to say that this model does have some limitations as it stands. So basically the rest of my talk is mentioning what these limitations are and how we might be able to address them.
Before you go on, can you talk a little bit better? So you say they're pinned, right?
Yeah.
That is a bit not very informative. So do they tend basically to align locally, or does the one see the other as a topological obstruction to its motion?
Right.
They try to pass through, or what
There is nothing to prevent them passing through topologically. It's purely a question of energy. So there is an energy barrier to prevent them coming apart. It's not impossible, but there's a cost associated with it. That's all.
So they can both break apart and pass through, and then
Yes.
reconnect again back.
Yeah.
But not with each other. It's impossible.
Okay. So
And another question is, this picture seems to imply the neutron vortices are mainly straight lines rather than...
no, it's the other way around.
Huh?
In this picture, the flux tubes are perfectly straight lines.
I thought that the straight lines are the neutron.
You are anticipating one of the limitations of the model that I'm about to address. So I'm going to mention what I would say are three limitations of this model, and then the rest of the talk will be addressing them in reverse order, for reasons I'll come to. So I've written them in this order because I think it's the sort of most apparent, perhaps. And you just mentioned the first one, in fact. Looking at this picture on the left, it looks like, wow, those flux tubes are really rigid, aren't they? They're perfectly straight lines, they're all equally spaced and so on. Is that for a good reason? Not really, no. In this model, they're just imposed. So in this model, the magnetic field and the proton fluid are just prescribed as functions of space independent of time. It's only the neutron fluid which is solved in time. Therefore, it's only the vortices that can move. And that's why it's only the vortices which are tangled. It's not for a dynamical reason. So why is that? And could we actually include the dynamics of the magnetic field and the proton fluid? Okay, that turns out to be a very difficult thing to do. That's why I'm going to leave it till last. The second point here, which isn't obvious from the picture, is that, and this is perhaps a bit controversial, and I've been told off by other people saying this, but I think the way that the entrainment is modelled in this work violates Galilean invariance, and I think that's an issue. It's going to take me quite a few slides to explain exactly what I mean there, but I will get to that. The final problem which actually is kind of apparent from looking at this picture, is that, well, there's about 12 vortices and about 12 flux tubes in this picture. Now, of course, we're not able to model 10 to the 18, let alone 10 to the 30, right? But 12 is not a very big number. And also, there seem to be equal numbers of 2, whereas really there should be 1 trillion blue lines for each red line, and so on, right? So we're way off in terms of parameters here. The other point is that you might look at this picture and say, yeah, I guess, fair enough, we're looking at a small piece of a much bigger system. No, this is the entire system, right? This model is a model of a spherical condensate with an actual spherical boundary, and it's only this big. So this is a neutron star that's like less than an angstrom across. That's what we're effectively using.
And do we know the tension of the flux tube, how it relates to the tension of the vortex?
I think the general result is that the neutrons have a stronger tension than the flux tube. So if anything, it should be the other way around. The red line should be straighter than the blue ones.
So that probably is not a factor because you have a trillion of them.
Right.
Whatever the tension is there, who cares? When you have a factor of a trillion.
Right. I think the argument that they make in the paper is that exactly that. Given that you've got so many flux tubes, it's reasonable to say that overall they're more robust. But having said that, in this picture, we don't have 1 trillion flux tubes. We have 12. Brilliant. So, yes.
Study dynamics was only study.
Right. So they have at least 2 papers on this. The first paper is just looking for the ground state, and you find the ground state actually looks like this. Right. You might expect to get just 2 lattices, but because of the entrainment, it all gets tangled up. Then they have another paper where they're looking at dynamics, but as I said, it's just the dynamics of the neutrons. The magnetic field and the proton fluid are still just fixed, independent of time. So it's dynamics, but it's limited dynamics. Okay, so I'm now going to try and address these 3 points in reverse order, starting with, why is it that we're only modeling 10 of these and not 10 to the 20 or something? Right. So in fact, from what I've seen, all microscale models of the neutron star core have always been global models in the sense that you model a finite system with a boundary and a small, or at least finite number of vortices or flux tubes in. Why on earth do we do this? Why don't we use a local model? For people who work in astrophysical fluid dynamics, this is normally what you do. I mean, I come from a background of stellar modeling where normally, a neutron star is tiny compared to most stars. So you don't have a hope of modeling the whole thing really in one go. So a very common idea is that you define some small local Cartesian box and you say, I'm not going to model the entire object, I'm going to model a small but representative piece and assume that everything around it looks more or less the same, so I'll use periodic boundary conditions. So why on earth isn't anybody doing this for neutron stars? Well, the reason is because the system isn't periodic. It's kind of a trivial point, but it's important. We know, for example, if you take a cross-section through the neutron vortices, even if they form a perfectly periodic lattice in space, we know that the order parameter of psi cannot be a periodic function of space because the phase, or the argument of psi, has to wind by 2 pi around each vortex. So that's what I'm trying to picture in this psychedelic block here. So this is a cross-section through a regular lattice of vortices. The black circles show the vortex cores, and the color shows the phase of the fluid on a kind of rainbow color scheme. So if you follow an anti-clockwise path around any of these black circles, you go once around the rainbow, from red to blue to green, back to red. And you can immediately see that this is not a periodic system. If you took 2 copies and stuck them together, they don't match at the boundaries. And there's nothing you can do about it. It's just not periodic. However, what is periodic is the relative velocity, by which I mean the velocity in the rotating frame. So it's not that the system is just completely aperiodic. It's just that it's kind of not quite periodic. It's
Relative velocity of what? Because you have only one fluid.
Right, here I have only one fluid. I mean velocity in the rotating frame. So I mean the velocity relative to
simply the velocity.
Well, depending on your frame, it's the velocity. Well, it kind of matters here because the gradient of the phase is the absolute velocity in an inertial frame. So you kind of have to make a distinction. Okay, so the system is actually what we can sort of call quasi-periodic. Given that the velocity of the rotating frame has to be periodic, and given that the velocity of the gradient of the phase, you can basically integrate that expression and quite easily derive this result that says if L is some translational symmetry of the system, so for example, L might be a vector between any two of these black circles, or indeed it could be either of the sides of this domain. For any such translational symmetry, then if you look at points separated by L, there must be a phase shift of exactly this form between them. This part just comes from the rotation of the frame, and then there's an arbitrary constant, which is not really arbitrary, and we don't know what it is. Okay, so we can't just use periodic boundary conditions, but we could use this as a boundary condition. So we could say this length is L1, this length is L2. We use these boundary conditions for some choice of C1 and C2. The problem is we don't know what C1 and C2 are meant to be, but we could just experiment. For some reason, nobody tried doing this until amazingly recently. I mean, this quasi-periodicity has been known about for decades and decades. But the first time I've seen it used as a boundary condition was only a few years ago. And what they found, so they just considered the 2D case kind of thing I'm plotting on the right here. The values for the constant C1 and C2 are essentially arbitrary. It just corresponds to shifting the picture left or right or up or down. So you basically just pick two numbers at random. It doesn't make any difference.
So what is n here?
Oh yeah, sorry. N, this vector is the number of vortices per unit area. The same thing can be done for flux tubes, but then you have to choose the gauge you're working in and so on. So it's kind of easier to think about vortices to start with, but you can do it all for flux tubes as well. Right, so in this picture, for example, if you want to know what n is, you just count the number of black circles and divide by the area of that rectangle. Okay, so that gets us sort of around the first problem. Now we can actually kind of do periodic box simulations of these things, except this is all assuming it's 2D. It's a little bit more complicated in 3D. It's kind of easy enough if you assume that your lattice is aligned with the third dimension, because then basically it's still a 2D problem. Technically, you now have three quasi-periodic boundary conditions, so you have an L1, an L2, and an L3. But if you assume that your array is aligned with L3, then it's easy to write down this vector n, the number of vortices per unit area. And we'd expect, this is a simple extension of the 2D problem, we'd expect that C1 and C2 will just correspond to lateral translations of this array. However, C3 is not arbitrary. C3 determines the phase shift between the top of the domain and the bottom. The velocity, remember, is the gradient of the phase. So if you impose a phase shift across that length, that implies there must be a flow along the rotation axis, which we don't want. So you can set C1 and C2 to anything you like. C3 has to be 0, or more precisely, it has to be 0 mod 2 pi because the phase is only defined mod 2 pi. Okay, so that case is easy. However, we know that in a neutron star, the vortex lattice and the flux tube lattice are not aligned. So if we want to model both of them together, okay, we could arrange our box so it's aligned with, say, the rotation axis, but then the magnetic flux tube will not be aligned with any of our Cartesian coordinates. So we just have to bite the bullet and consider the more general case of a tilted lattice. So we have to extend these results. Okay, so what's quite easy to figure out is what this vector n has to look like. If this is meant to be a sort of periodic system, then each face of our cuboid domain has to be intersected by an integer number of vortices. So we now have three integers, n1, n2, and 3. And with a bit of geometrical reasoning, you can figure out that the number of vortices per unit area is given by this expression.
I don't take only one vortex, because we need a trillion of flux tubes. We're not going to look at a big volume, we'll have a close one, right? Not be realistic. Right?
I agree. So for one of your lattices, you might just take one.
Yeah. Right.
The problem is that
increase the number of flux tubes as much as you can.
Right, exactly.
More realistic.
In practice, you would probably have 1 or maybe 0 vortices in your domain and a bunch of flux tubes. Mm-hmm. If you're going to do that, actually, perhaps somewhat counterintuitively, it makes more sense to align your domain with the one vortex than it does to align it with all the flux tubes. Because if you wanted to do one vortex tilted, it's kind of inevitable that you'll actually have more than one. Like if you try to just have one like this, actually it's going to reappear over here. So if you want to have as few vortices as possible, it makes more sense to align the domain with the one, even though that seems a little bit weird. If you want to have them as far apart as possible, you actually give them priority. Anyway.
Can I just make one comment?
Yeah.
So basically a caution when you actually do this calculation. Because yes, you can put your box in periodic boundary conditions. This doesn't mean that that is what really happens. Because if the box gives you a scale, which is different than the scale of the system, basically these cubes, they cannot really be periodic.
Well, they can be, but they wouldn't be.
You have a very big system. Inside this very big system, which actually isolate the part of the scales of that system. There's no reason why this box will be periodic, because what happens with other scales, it doesn't really necessarily is a replication of what you have inside the box.
I agree completely. Of course, this applies also to classical fluids.
It's not
done in local models.
I'm not saying that. I'm not saying that you keep that in mind.
I agree. To put it another way, you could say that we are imposing long-range order on a system that we know probably lacks long-range order.
I think with the classical fluids, it's not exactly the same thing, because with classical fluids, you can get a tube size, which can give you some realistic non-dimensional numbers. That is, numbers which are actually found in real experiments. So the periodic box there is not a drastic approximation.
Ooh, I'm not sure I completely agree, but maybe we can discuss it later. Okay. I mean, the hope here, of course, is if you make your box big enough, hopefully it doesn't really matter anymore. But I mean, that's a hope. That's not something you can ever be 100% sure of. Okay, so if we want to have a tilted array of vortices or flux tubes or whatever, then we need to specify 3 integers. We now know what n is, but the question is, what about our 3 values of like C1, C2, and C3? Well, by analogy with this sort of 2D version, we would imagine that of those 3 degrees of freedom, 2 are essentially arbitrary, but the third isn't. So once you choose C1 and C2, you're not free to choose C3. There's probably a unique value. And if you choose it wrong, then you're effectively imposing a flow along the rotation axis that you don't want. So we imagine that there is a condition on these 3 numbers. And indeed, it turns out that there is. And you can write it like this. So n1 times c1 plus n2 times c2 plus n3 times c3 has to be equal to this, modulo 2 pi times the greatest common divisor of n1, n2, and n3. This may well be a standard result in like lattice gauge theory or something, but I have no idea. I'm not in that field. And I asked a few people and nobody could tell me. So of course I had to spend a few weeks deriving this. And then at the end of it, I realized that you can get it in about 2 lines if you're smart. Such is life. Never mind.
It
was tempting. No, what it is, I wrote a paper where I pretended I'd done it in 2 lines, whereas it actually took me 4 weeks. Okay, so the point is, of course, no matter how long it takes you to come up with these boundary conditions, do they actually work? Luckily, they do. So here's a kind of proof of concept. This is not interesting physics particularly. It's just to prove it works, right? So, so what we did here is we just take the Gross-Pitesky model. We solve it in imaginary time, by which I mean we're just doing a simple gradient descent to try and find the minimum energy state. We start with complete random noise. We impose our quasi-periodic boundary conditions. So we're imposing the number of intersections of the vortices of each face. I think it was 16, and 16, just chosen at random. And I'm going to show you a movie of what happens as the system relaxes towards the ground state. Hopefully. Here we go. So I will pause it because everything interesting happens immediately and then nothing interesting happens after that. So, okay, so we start with complete random noise, so it just looks like a mess. Almost immediately, of course, it forms a bunch of vortices. They're initially very tangled because we started from a noisy state. So there's all kinds of intersections and crossings and tangling and so on. And as we evolve this towards the ground state, you'll see they all reorganize, they straighten out, they reconnect. Various reconnection events happen. And then it kind of settled down and nothing else. So at first I was kind of surprised by this. I was expecting the system to reach its ground state, which would be a rectilinear array of perfectly straight vortices. It never gets there. The movie's still running, but it has completely reached the steady state at this point, and nothing happens. So the point is that these things are completely free to reconnect, but there's a kind of barrier to that, because if they're too far apart to start with, you need to do work against tension to bring them together before they can reconnect. In other words, what we found is a metastable state. It's a local minimum, it's not the global minimum of the energy. And I think
you fix volume a day once in a while to get out of the middle.
you could anneal the system, I'm sure. We haven't yet. We may or may not. I mean, this is not really intended to be a physics simulation. This was just to check if the boundary conditions work, right? But actually, it's kind of interesting that when you have a complicated enough tangle to start with, it's almost inevitable that it's not going to untangle itself completely. It's almost inevitably going to get trapped in a state.
You can start from the initial arrangement of vortices, regular, calculated energy,
right,
and see how it compares with this. Did you try that?
We haven't yet, but we will.
Because that would be
I would imagine that it's slightly lower, but not much lower, right? I mean, I think these things are very nearly straight. They're only slightly tangled at this point. So I think what we're showing here is that this system is glass in the sense that there are probably many local minima with very similar energy to the ground state.
So, how does the system decide how many vortices it has to create?
Okay,
Which orientation?
The boundary conditions impose the number of vortex intersections with each face. But the arrangement within the domain could be kind of anything. Also, when I say the number of intersections, I mean that's like counting plus and minus. So, I mean, you could, in theory, instead of having 16 intersecting this face, you could have 17 plus one going the other way, and it would be the same. Of course, in the ground state.
So it's the same thing as having just, a rotating frame.
Yeah, exactly.
And then you have finite angular momentum, and so you find the lowest energy with that angle.
It is basically that, but slightly more prescriptive, because you are geometrically constraining the system to a certain extent.
Right, because of the
not only by the angle, but also by the size of your domain.
Right.
So actually, an interesting question is, there are different lattice configurations. Are we effectively imposing the lattice configuration? And the answer is yes and no. It sort of depends on how many vortices there are. So this was on my last slide, but I didn't mention it. I'll just mention it very quickly. There's a standard result in a 2D Bravais lattice, or a lattice of points, that if you want to draw n points in your rectangle, how many lattices can you form? The answer is the sum of all divisors of n. So if n is 6 vortices, there are 1 plus 2 plus 3 plus 6 equals 12 lattices. The generalization of that to this problem with a tilted lattice is that it's the sum of all common divisors, n1, n2, and n3. Again, I have no idea. That's probably a famous result, but I didn't know where to Google for it.
You took a cubic box, which is kind of a limitation in this case. I think that changing the height would be a reasonable thing to do. You see, and make it very long. You see, because you see the height in principle, you see the result is independent of height, because they are more or less aligned with the vertical direction. But if you change that, you see that you might think something different. In my opinion, they are not necessarily straight. They start bending a bit. You see, and they go around each other, or whatever. You see.
Right. I mean, it's definitely true that if you redid that simulation in a longer domain, it would not look quite the same. Right.
Yeah,
Certainly.
so for that reason, anyway.
You can choose whatever domain size you like, though. Right. The boundary conditions still work.
No, I
doesn't assume it's
GSC, but what you get, you see the result is different. And how different.
True. Yeah. That's what the referees asked as well. So that's something we are going to look into. Right? So anyway, so I haven't put this on the archive yet, but I will if anyone's interested. I can send you. Okay, so that's the first thing. I've got 2 more to go. Maybe I'll skip a few slides at some point. So we can now do local sort of periodic box simulations of these things. That's nice. We need to include entrainment, and I made a slightly perhaps controversial statement, but I don't like the way the entrainment's included in most of the existing models. So I just want to sort of justify that a little bit. Okay, so people get upset when I use the phrase Galilean invariance because they tend to tell me, yeah, but my model is Lorentz invariant, so I don't care. So, okay, I'm going to use the phrase local phase invariance, which actually is more general anyway. So it's a standard thing in like condensed matter theory, I guess, that the strong interaction which leads to this entrainment satisfies this local phase invariance principle, which basically is a fancy way of saying that the interaction between your two superfluids only depends on their relative velocity, which is kind of obvious when you think about it, but there you go. So what that means in practice is that when you write down the free energy of the system, the velocity dependent part of the free energy has to have a form like this. So you have the kinetic energy of the proton fluid plus the kinetic energy of the neutron fluid plus any interaction energy, and that has to depend only on the relative velocity, or technically gradients of the relative velocity, if you want as well. Okay, so that's fine. So this has been known for a very long time, I guess. The problem is that most models for the neutron and proton superfluids in the core are kind of mesoscale or macroscale models, in which you're not worried about resolving individual vortices and flux tubes. You think of them as infinitely thin lines, and the density is basically constant. So what people tend to do is expand out this third term and combine the two v squared terms with the existing ones and say, well, it's just the same as renormalizing the mass, isn't it? You know, instead of writing the interaction in this form, we can equivalently write it as this dot product, and we just have to slightly change the values of the proton and neutron mass, and it's the same thing. The problem is that's only true when these coefficients are constants. So it's only true when you neglect the fact that the density goes to 0 in the core of a vortex or a flux tube. If you try and use this form for the interaction energy in a microscale model, then you violate local phase invariance, which is sort of equivalent to Galilean invariance in this case. And I didn't say this, Nicolas Chamel said this. So if you don't like the idea, you can complain to him. He said this a long time ago, but I think people have kind of forgotten because pretty much every model I've seen for the entrainment on the microscale model assumes it looks like that, including the picture I showed earlier. So how should we actually include entrainment in a microscale model?
That's an interesting statement because nearly all models of hydro have the other form.
Really?
Yeah.
Well, they're
I can't think
equivalent.
of anyone that
In the hydro model, they're equivalent because you're not taking into account.
I understand what you're saying, but I mean, the starting point for I think pretty much every hydro model I can think of is the top line.
Okay, fair enough.
Analogy of the top line. I don't think anyone would go.
Maybe you go to different libraries.
So, okay, so why is it that in microscale models people have written it this way? The reason is because it's so much easier.
Yeah.
Right? It's very easy to compute this term. It's, as I'm about to show on my next slide, it's a real pain in the arse calculating it down.
Oh, I'm sure.
So,
Well, you have to simply translate the entire system in the correct mass of the entire system. And you'll obtain that only in the first line of the second. You can do it arbitrarily.
So, how, in a microscale model, how can we include entrainment in a way that's consistent with local phase invariance? Okay.
It's a separate question. Is that minus sign here relevant or not?
Oh, in the first line?
Yeah.
Yeah. So the wonderful convention in this subject is that this thing is defined to be negative.
I'm sorry.
Rho Pn is negative by convention.
Okay.
Yeah. Don't blame me. If it was up to me, it would. But it is. There is a good reason. It's because people don't usually write it in this form to start with. They write it as their entrainment matrix. So normally it's written as a 2 by 2 matrix, and then you have the diagonal elements of your Rho Pn. Right. So there's a logical reason for it, but physically it's extremely annoying. Yeah, the three terms are all positive, definitely. Okay, so really the sort of Gross-Pitevsky or Ginzburg-Landau model is a mean field model, right, where you expand everything in powers of psi and derivatives and so on. So the real, I think the question is, if you want to include entrainment in your model, to what order do you need to go? The answer is you need to go to second order in density and second order in derivatives. So what is the most general term we could put in the free energy at that order, which is consistent with local phase invariance? The answer is this. There are 4 free parameters, which I've called G1 to G4. And if in principle, there's no reason why you shouldn't have all of these, right? In practice, of course, it's a real ugly mess, and that's why people don't do this. But there's no sound justification for keeping one of these and throwing the others out. Basically, the first term is the only one that actually involves the velocity. So in a sense, the first one is the entrainment term. The others just involve density gradients. So people sometimes call these density gradient terms, and they usually leave them out. But when you think about it, the first term also involves density gradients. They're just a bit different. So there's no real justification keeping this and throwing these away. What people tend to do is they just keep this bit. That's the v dot theta. Okay, so a priori, there's no reason why we shouldn't have all four of these, but if we're going to do that, we need to find values for them. Where on earth are we going to find values? Well, you can go to a more complicated, maybe I should say more realistic model, such as some kind of density functional theory, like the Skirm functional theory. That has all the extra physics, spin orbit coupling, all the other kind of stuff that I've been ignoring. So suppose we take the Skirm density functional model and we just throw away all the bits that I haven't included. It turns out you can write it exactly like this. You have all four of these terms, none of them are zero. And in fact, when you work out the value of the coefficients, G1, the one that people normally care about, is an order of magnitude or two smaller than the others. So there's absolutely no justification in throwing away the second line and keeping the first one. Okay, so what if we just take those numbers and run with it? What kind of problems might we look at? Well, an obvious problem to look at is the nature of superconductivity. By the way, how much does it matter if I overrun?
Well, let's try and get to a conclusion because we have discussions later. But
okay.
But you can
because I can basically skip a lot of stuff and finish on time, or I can not. It's kind of up to you.
Being intelligible or not?
Sorry, is it
The choice between being intelligible?
Oh, I don't know if that's a choice. I don't know if that's. I can be intelligible and fast. No, no.
Okay, well, what I'll do is I'll stop you at 11:30 and give people a chance to leave if they want to.
Brilliant. Okay, so I tell you what I'll do. I'll just give the conclusions of these bits, and then if people have questions, I'll come back to it. So an obvious thing to look at is the nature of superconductivity. The simplest case of a superconductor is the Ginsburg-Landau, like for a single component superconductor. And there are two length scales that come in, the size of a flux tube core, psi, and the size of the magnetic kind of skirt around it, lambda. And whether you get type 1 superconductivity or type 2 depends on which of those length scales is longer. Type 2 is where the flux tubes are mutually repulsive, so they're kind of dynamically stable. Type 1 is where they're mutually attractive, so they tend to kind of coalesce into patches of magnetic flux. And an easy way to visualize this is to plot the energy of the system as a function of d, the average distance between flux tubes. If it's type 2, you can minimize the energy by pushing them further apart. If it's type 1, you minimize the energy by bringing them closer together. Okay, so an obvious thing to look at is, what about if we now include the effect of entrainment? That will change the structure of the flux tubes, and this could lead to different kinds of superconductivity. There's a couple of papers at least looking at this, all of which violate Galilean invariance. So what about if we do it in the way that I mentioned on my previous slide? If we include all of these entrainment terms from the Skirm model, then what happens? Well, then what you get is a picture more like this, which actually is pretty much in agreement with what these previous papers found. So violating local phase invariance may not make that much difference in the end. But still, what you find, which I think is interesting, is that, well, first of all, the transition from type 1 to type 2 happens only for a larger value of lambda, which could be important because it means that the size of the type 2 region in the neutron star core might be a lot smaller than we normally think it is. So 1.2 is somewhat bigger than 1 over root 2, and that is kind of significant here. And the other point is you do indeed get type 1.5 superconductivity, which means that on large length scales, flux tubes repel each other, and on small length scales, sorry, they attract each other, and on short length scales, they repel each other. So they have there's a minimum of some finite separation distance. So Vanessa mentioned this towards the end of her talk yesterday, and it means that you can get domains of flux tubes. So you get a patch of flux tubes here and a patch over there, but none in between. Okay, so the final thing I wanted to address, I only have 2 more slides, so I might even finish on time, is the most difficult question of all, if we want to have a full dynamical model, including not just the evolution of the neutron fluid, but also the proton fluid and the magnetic field, how do we do that? Well, the good news is that if we're happy with being able to write the free energy as a function of the order parameters and the magnetic field, then it's very easy to derive your equations of motions for your two superfluids. That's just trivial. What's much more difficult is the evolution equation for the magnetic field. We're in a physical regime here where the superfluid velocities are much slower than the speed of light, at least. So it's basically kind of MHD type regime. So what we need is an induction equation. We need to, in other words, somehow find a closed form representation for the electric field in this system. And the standard way of doing this in MHD is that you consider the balance of forces on your electron fluid. E is kind of one of them. Whatever other forces you think are important, you stick on the right-hand side. And if you can evaluate them, then bingo, you've got an evolution equation for A. How can we do this in the neutron star core? Well, we almost immediately run into problems because, first of all, on the scales we're looking at, we're much, 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 much smaller than the electron mean free path. So it's not really a fluid at all. That's kind of an issue. But let's suppose we just ignore that and persevere. What terms might we want to include on the right-hand side here? Well, there's many. I mean, maybe the Lorentz force on the electron is important. Maybe their inertia is important. Maybe we'd like to include some kind of drag. We know that the scattering of electrons is the main dissipation source in the core. But how should we actually include that? I don't know. I would like somebody to tell me. I was reminded yesterday that we do know quite a lot about laboratory superconductors. So what do laboratory superconductor models do? Well, there it's kind of easy. So you just say that the total normal current in the system you can calculate quite easily. And then you just use Ohm's law. You just say that the only important force in the laboratory superconductor is the drag on your normal electron current, right? So your electrons are being scattered by the material of your superconductor. That gives you a drag force in the laboratory frame, just proportional to the velocity of your normal electrons. And those are the only normal components, so that's proportional to the electric current. And then you shove that in here, and it just gives you a closed equation for the magnetic field. The problem is this is not really at all appropriate for the neutron star core, because what we don't have in the core is some kind of background of ions that our electrons can be scattering off, right? We don't have a preferred frame. So even if you wanted to do sort of the simplest thing here and just say, oh, we just put the drag force on the electron fluid, you have two problems. First of all, you don't know what the electron velocity is. It's not just proportional to J, because there's also no normal protons. And secondly, if you want to include electron scattering here, you need to say what they're scattering off. And it's not just some stationary material. And in any case, it's not really electron fluid at all. Okay. So this is why it's difficult to have a fully dynamical model for this problem. And I have some ideas, but I would greatly appreciate any work insight.
Just follow kinetic description for the electrons, just like the transfer equation for the probability as a function. I mean, that's because that as I understand the box is so small that the electrons are not really hydrodynamic system there. It's correct.
Well, the problem is just that their mean free path is very long.
Right.
So you could solve the Boltzmann equations.
Yeah. So why don't you just take kinetic description for the electrons?
The problem is that trying to describe the interaction between that fundamentally classical system and the quantum system is not that straightforward. That's probably what we should be doing, but actually doing it is not easy. That's the problem. Okay, so if I could just, so I can pretend I was on time, I will just say, here's my final slide. Why would I even bother doing all this if it's that hard? Well, because I think there's lots of interesting things we could look at, which are quite relevant to understanding neutron stars. Here's just a couple of which have already been mentioned earlier on this week. There's various interesting questions, such as what is the time scale for the evolution of the flux tubes? We know that the true ground state in the neutron star would be to expel all of the magnetic field from the core, but we believe that it would take billions of years to do that. So in practice, it never gets around to it. But what do the flux tubes actually do then? Do they How do they look in the different regions of the core? We don't really know. Another point that's been made by Bennett Link is that if you consider a material with a load of elastic strings in, the kind of configuration, the geometry of the strings has a big effect on the macroscopic properties like elasticity of the material. In other words, cooked spaghetti behaves very differently to raw spaghetti. So if you think that your flux tubes are all perfectly straight, then that tells you that you have a very anisotropic kind of stress-strain relation in the core. Whereas if you think that they form a whole bunch of tangled nets, then it's probably a much more isotropic system. And there are other differences as well. Maybe we could detect the difference from looking at oscillations in neutron stars. And as has also been mentioned a couple of times earlier this week, to explain the biggest glitches that we see in some pulsars, it seems as though you must invoke some kind of pinning within the outer core of the star, pinning between the neutron vortices and something. Maybe it could be pinning of the vortices to the flux tube, but it really depends on how strong that pinning is. And the only way to evaluate that is with a fully dynamical model. You can't just solve for one component. Really. Okay, so I'm almost on time, and I'll stop there.
You never mentioned Coulomb interaction. You have charged protons.
Yep.
You'll have at one point charged electrons. And you can neglect that only if you assume that the density never changes for both of those, if some kind of Gilliam model, which probably is not correct. So, so I think there should be a big element that should be included in this type of treatment.
Okay, I think it's reasonable to assume that the system remains charge neutral.
Well, large scale, yes, but not on micro scale.
Whether it's true on this scale or not,
yeah, it's the density. For example, you see the density of the protons is not constant in your model. It's not.
No, but the model is only for the superfluid protons. So there are also normal protons residing in the cores of the flux tubes, which are not even included in the model.
You see, that is going to modify the stiffness of the proton fluid.
Yeah.
The Coulomb interaction.
Okay. So normally what people do in laboratory superconductors is they do assume it's charge neutral. And they say that you do have normal and and quantum components, but overall they kind of balance each other out, so you have a more or less uniform density of charge. I'm kind of assuming that can also be done here, but you might be right.
Well, you assume, but what's the effect of that?
Yeah,
indeed. You have to say, what's the error doing?
So the real issue here, so it kind of relates to your question as well. It's not that hard to include the effect of the quantum components on the classical components. It's much more difficult to do it the other way. So the Grothe-Vitesky model, or whatever you have, the formalism that we're using to describe the superfluids is intrinsically Hamiltonian. It's very difficult to include the effects of interaction with the non-quantum components in that. That's what's really difficult. So you can have a kind of one-way interaction. It's much harder to have a two-way interaction model, just because of the mathematical formalism we use.
But that is not something that is not being done. You can get ideas about it.
Yes.
If you go, for example, dilute gases literature, there are models where quantum concentration is coupled to the compensation.
There are
coupling is done by the fixed fluctuation mean field terms in the equation for the ground state.
Yes.
And then there is also details there of how this is done. Basically, it's the collision integrand that's the most important, and that has this information about how some of the interactions between.
Yeah. Okay.
So
that's true. So this kind of thing is looked at normally in the context of thermal excitations, right? So normally in the context of your superfluid and your normal fluid.
Right.
Whereas here it's slightly different, but maybe the same techniques can be used.
That's what I mean. I know it's slightly different, but maybe something similar you can do.
That would be great. I have very little expertise in that particular area. And I know that their models are quite complicated. But so I'm based in Newcastle, and there's a number of people there who are looking at exactly this kind of thing.
You're in the right place.
So I'm hoping that they can help me. But first I have to sell them on the idea that neutron stars are neutron.
So do we know plasma frequency for this electron proton system? So this is referring to our question.
Well, that would be pretty hard. That doesn't exclude static deformation. You see, plasma is dynamic.
Yeah.
So you're talking about those. You know the density of protons that we infer once through the plasma.
Yeah, I mean, we know the parameters, so you can estimate whatever quantities you want. But there's a lot of different components here. There's a lot of physics going in. So the question is, like, what numbers do you need to compare with what other numbers? That's a very vague answer. But yes, if you want, we can figure out all the plasma frequencies here.
Any other questions?
So I have one. So when you finish this,
yeah,
at some point in the future,
yeah,
indeterminate quantity,
right,
you're going to have to move on to the real question.
Yep.
Which is, how do you average over this result to get the microscale model?
Right.
Right. I guess some of the tools to develop might be helpful in that respect.
Mm-hmm.
But I don't know exactly.
Okay, right.
Does that make sense?
Absolutely. That is exactly the question. So I completely agree with what Bryn Haskell said in his talk last week. That you probably have to have some kind of hierarchy of models, right? So you probably can't do a single simulation with like 10 or even 100 flux tubes and then say, right, now just put this in a neutron star calculation. You know, what you need to do is decide what are the right questions to ask. So here's a few examples. Something you can easily do is say, if I take my array of flux tubes and now I perturb it, how stiff is it? How does it respond? So the simplest thing you can do is say, if I do the simulation and now I do the same simulation but make the box slightly bigger, so everything's slightly more stretched out, which has more energy. I mean, that's an extremely easy thing to compute. And essentially what you're doing is you're asking, what's the elastic modulus of this flux tube array? How does that depend on entrainment? How does it depend on whether it's a tangle or not? Those kind of things you can easily do. And they directly feed into these kinds of questions. What is the frequency for oscillations of the core? Then of course you have to ask, can we really measure the oscillations of the core?
Yeah.
Are there other uncertainties in that?
In a sense, that's true. But the reality there is that there is no, for the stuff that is in the link and Einstein discussion, there is no macroscopic model that describes how this should work. The stuff they write down is nonsense. I mean, the idea is fine, but the equations they write down is just correct.
Sure. Okay.
And so I mean,
okay, but that's a problem with the macroscale model.
No, that's right. But I think that's an important point.
Yeah.
What you need, I think, is to think what you're doing is the right thing. Yeah. But someone also needs to think about what is the macroscale model that's going to meet this.
Yep.
And then one has to figure out how do I establish that when the overlap between the two, when they sort of one takes up the effective average model actually describes the kind of thing you see. You know what?
Yeah, I totally.
That's what's missing, right?
Exactly. So I think in between the 10-kilometer scale and the 10 to the minus 12 centimeter scale, there's a lot that's going on, and you probably need at least one intermediate mesoscale model in between.
I don't think so. I think you need a statement of what is a fluid element, in the sense of the fluid dynamics model, the microscale model is a fluid model. It says I've averaged at this scale, right? Mm-hmm. And that you can ask what that has to mean, right? Yep. It has to mean a model that contains more than one vortex, for example. So it has to have a bunch of vortices where you can have a meaningful average. Mm-hmm. So you simply have to ask, what is the largest scale I have to account for in averaging, right? And then on that scale, you have a smaller scale, we'll say the flux tubes, you can average on a much smaller scale, right? Right. And the question is it meaningful to ever do that? Or do you only ever say the fluid element is, say, a box that contains 100 vortices or something like that across? Or something, or 1,000 or 10,000, whatever. Okay, I think then you've got pretty large fluid elements. You've got sort of centimeter scale at least.
Yep.
And that's quite big.
Is that large?
Well,
compared to
quite
this,
big,
it's
quite
large.
big for fluid dynamics.
Well, if I can say something about that. There is I think what is important here to realize is that unlike a typical aerodynamic modeling, where you can define easily, let's say, something like a fluid element, simply because there is a separation scale between the thermal and the hydrodynamic scales. The problem is that you have a continuum of scales. It is not easy to choose where should I stop my average, simply because there is no gap in the scales.
I think that's true.
So basically, the approach would be pretty much like what we do in statistical field theory, where we have some renormalization procedure. But this renormalization procedure, it will also require a long range of scales with some similar dynamics.
Right.
So these are non-trivial questions that I agree that these are very essential questions, but it's not so easy to answer.
Or you just have a really messy theory where all the coefficients depend on the scale that you're doing your hydro.
Well, I think, okay, so I agree with you, but I think in response to Niels's point, there are special scales in this problem that are well separated. There is the separation between flux tubes, which is, 10 to the minus 10 centimeters or something, right? That's the kind of scale I've been talking about here. That's what I mean by microscale. There's the separation between vortices, which is like 10 to the minus 5 centimeters. That's much, much bigger. I would call that the mesoscale. And then there's the hydros, the true hydro scale, which is enormously bigger. Okay, I feel that you need to have a hierarchy where you average to one scale, you understand that, and then you implement that as a parameterization in the next scale model, and then you average over that and implement that in the next scale.
That's right. So let me so you talked about MHD, right?
Yeah.
The model you're doing now is never MHD. There's no MHD because the electrons are ballistic. This scale you're talking about, there's no sensible sort of average flow, whatever, that leads to MHD. So it's clearly not MHD. On the meso scale, where you say average over the electrons, mean free path, that sort of scale, you can talk about MHD.
Sure.
So I think it could be that a different model that started on the meso scale somehow would be easier to deal with than this.
It would be, except that then you'd have to parameterize entrainment in the mesoscale model or something. And if you're working at the mesoscale, presumably you'd have to average over 1 trillion flux tubes.
Of course.
Right.
So I'm not,
How do you do that?
I'm not saying you don't need, you still need this, right?
Yeah.
But I'm just saying you need to worry about both. They've got different challenges.
I agree that including the electrons properly is much easier to do on the mesoscale where they're actually a fluid. And also, it's not quantum anymore. It's essentially a classical system, so it's very easy to do the two-way couple.
Well, sure. I'm just saying.
It's always going to be very hard to include electrons in this scale.
Yeah, absolutely.
But there are electrons, and they are having an effect on this scale. And we can't just ignore them.
No, that's absolutely right. It's just you have no, I mean, the starting point for how you do this, not obvious. It's certainly not MHD.
It's not MHD. Well, it depends what you mean by MHD.
Well,
we could get into an argument about that.
In any sense.
It's MHD in the sense that it's non-relativistic.
That's not an MHD. MHD involves statements like quasi charge neutrality and things like this, which we clearly don't have. Right? Individual electrons shooting through, they're clearly charged. There's no meaningful sense of charge neutrality.
Oh, you say individual electrons, but I mean, you're not talking about the mean free path there.
No, I'm talking about bullets shooting through your sphere, right? I mean, I'm just saying. I think it's much harder. I don't even see where you would start.
I agree that it's not fully MHD.
Not at all. It's nothing.
There is a certain starting point.
I mean, we say it's MHD because that's the only thing as
we know how to do.
We understand about electromagnetism. But that's, it doesn't mean that that's the right thing to do.
He's right. I mean, the MHD requires a lot of assumptions about your system. Certainly, if you see the level of ballistic electrons.
Yeah. No, I agree. I agree that normal MHD requires 3 or 4 assumptions, and at least 2 of them are not valid here. That doesn't mean all 4 of them are not valid. That's all I'm saying.
No, but if you break one of those assumptions, you don't have any scale. Let's
Yeah,
do that
okay.
later. I mean, it's a very important
Let's
point.
discuss this later.
Yeah. Okay.
Okay.
Thank you. Thank you.